Yesterday we have completed up to sixth problem. This is the next problem. What is given? A particle is dropped from a height h. The de Broglie wavelength of the particle depends on its height as. So a particle, whenever it is dropped from certain height h, it is dropped from certain height h. What about its velocity? V is equal to square root of 2gh. 2gh. V for velocity. Velocity is equal to square root of 2gh. We know de Broglie wavelength. De Broglie wavelength. De Broglie wavelength. Lambda is equal to h divided by mv. In the place of this v, we'll substitute here. In that place of v, we'll substitute square root of 2h, square root of 2gh. Therefore, we'll get that lambda is equal to h divided by m into square root of 2g into capital H. 2g into capital H. So the lambda is inversely proportional to square root of h. So lambda is inversely proportional to h power 1 by 2. On bringing to the numerator, lambda is equal to, lambda is proportional to h power minus 1 by 2. B option is correct. Next problem. The de Broglie wavelength of an electron accelerated through a potential difference of 400 volts is approximately. So de Broglie wavelength of this electron accelerated through a potential difference. For us is given potential difference V is equal to 400 volt. V is equal to 400 volt. Then lambda is equal to h divided by square root of 2m into VQ or kinetic energy. Kinetic energy we can write VQ or EV. Q for charge of charge. Here E for charge of the electron. Then lambda is equal to h is 6.63 with approximately like 6.6 into 10 power minus 34 divided by square root of 2 into mass of the electron 9.1 into 10 power minus 31 kg. 9.1 into 10 power minus 31 kg. Okay, into charge of the electron 1.6 into 2 into mass of the electron 9.1 into 10 power minus 31 kg into charge of the electron 1.6 into 10 power minus 19 into potential 400. Therefore, lambda is equal to what we'll take the lambda is equal to 6.6 into 10 power minus 34 divided by this one. On simplifying, you have to simplify this. On simplifying this, we will get 0.61 into 10 power minus 10 meters. That will write lambda is equal to 0.06 into 10 power minus 9 meters. Then lambda is equal to 0.06 nanometer will come. This is lengthy calculation, you have to do that. This is this 10 power minus 31, 10 power minus 19. This is the 10 power 34. This is 10 power plus 2. So this 2 into 9, 18. 18 into 4, 18 into 4. 4. 72. 72. 18 into 4, 72. 72, it's nearly 75, like that will come. Okay, after simplifying this, we will get it as 0.61 into 10 power minus 10 meters. And again, we have to rewrite like this. So light have two different frequencies whose photons have the energies 1 electron volt and 2.5 electron volt respectively. Successively illuminate a metallic surface whose work function is 0.5 electron volts. Ratio of maximum speed of emitted electrons will be. Ratio of the maximum speed of the emitted electrons will be. Ratio of the maximum speed of the emitted electrons will be. This is a work function is given. Given data, if I write that frequencies, different whose potentials have, whose lights have two different frequencies, whose photons have energies. Energies are given. Then energies are given. We need to calculate ratio of maximum speeds. Work function is given. W is equal to 0.5. W is equal to 0.5 electron volts. W is equal to 0.5 electron volts. So then E1 is equal to 1 electron volt. E2 is equal to 2.5 electron volt. Then we'll write that kinetic energy Ke is equal to energy E minus work function W naught. Then half M V maximum 1 square is equal to E1 minus W naught. We substitute this half M V maximum 1 square is equal to E naught means what? 1 electron volt. 1 minus work function 2.5. So therefore, this is the, let us suppose equation number 1. Is the 1.5, 0.5, sorry. 0.5, not 2.5. 0.5. 0.5 means we will get half M V maximum square is equal to 0.5. 1 by 2 M into V maximum 1 square is equal to 1 by 2. Equation like the second equation. M V maximum 2 whole square is equal to this is 1, not 2.5. E2 is given as 2.5. 2.5 minus 0.5, that will be equal to 2. 1 by 2 M V maximum 2 whole square is equal to 2. Equation number 2. Equation 1 by equation number 2, if I write. Equation 1 by equation number 2, if I write. V maximum 1 square by V maximum 2 whole square is equal to 1 by 2 divided by 2. This will be V maximum 1 by V maximum 2 whole square circle. That will be equal 1 by 2 by 1 by 2 into 2, 1 by 4. It is under square root. V maximum 1 divided by V maximum is equal to 1 is to 2. 1 is to 2 is like this. Next problem. Find the de Broglie wavelength of electron with the kinetic energy 120 electron volts. Kinetic energy is given as 120. De Broglie wavelength is to be calculated 120 electron volts. Then we have tried that in that equation. Given data is potential V is given as 120 volts. Then what's the formula for it? De Broglie wavelength lambda is equal to H divided by square root of 2m into K. Then lambda is equal to H is 6.63 into 10 power minus 34 divided by square root of 2 into mass of this de Broglie electron, they told 9.1 into 10 power minus 19 into kinetic energy is given as 120 electron volts. 120 volts, not 120 electron volts. That will be equal to 120 into 1.6 into 10 power minus 19 volts. One 120 to 1.6 into 10 power minus 19 volts. Therefore, lambda is equal. On simplifying this full, we will get 1.12 into 10 power minus 10. So the lambda is equal to 112 into 10 power minus 12 meters. So lambda is equal to 112 picometer. 112 picometer. Next. The maximum kinetic energy of the photoelectrons depends upon maximum kinetic energy of the photoelectron depends upon its a frequency. Maximum kinetic energy of the photoelectrons depends upon its frequency. So incident frequency is more, then more number of with kinetic energy, more kinetic energy electrons will be emitted. So maximum kinetic energy of the photoelectrons depends upon frequency. The maximum velocity of the photoelectrons emitted by metal of 1.8 into 10 power 6 meters per second. Take the value of the specific charge of the electron is 1.8 into 10 power 11 coulomb per kg. The stopping potential is. So the kinetic energy and stopping potential, they are related as. What is the given data? First we'll see. Maximum velocity of the photoelectrons emitted by metal of velocity is given. Velocity V is given as velocity V is equal to 1.8 into 10 power 6 meters per second. Take the value of specific charge of the electron is specific charge. E by m is taken as 1.8 into 10 power 11 coulomb per kc. Then the stopping potential is, take the value of specific charge of the electron is 1.8 into 10 power 11 coulomb per kc, then stopping potential. We need to calculate the stopping potential. For this stopping potential, that depends on maximum kinetic energy. Maximum kinetic energy is equal to EVS. E for charge of the electron, Vs for the stopping potential. So half m V maximum square is equal to EVS. Then we have to calculate what is that stopping potential. So Vs is equal to m by E 1 by 2. Vs is equal to 1 by 2 into m by E into V maximum square. Then Vs is equal to 1 by 2 into mass of the specific charge is E by m is equal to 1.8 into 10 power 11. But here what? Mass by charge is there. So reverse 1 divided by 1.8. 1.8 into 10 power 11 into velocity. What is the velocity? 1.8 into 1.8 into 10 power 6. Whole square is there. That's why 1.8 into 10 power 6, 2 times I have written, because it is a whole square. V maximum square is there. Then 1.8 to 1.8 get cancelled. 2 that cancel and 1.8 to 0.9 times. This 10 power 11 comes to numerator. So Vs is equal to 0.9 into 10 power 12 into 10 power minus 11. Therefore, Vs is equal to 0.9 into 10. So Vs is equal to 9. Next problem. The additional energy should be given to an electron. The additional energy should be given to an electron to reduce its de Broglie wavelength from 1 nanometer to 0.5 nanometers. So that additional energy is needed. Additional energy is needed. This is a little bit lengthy, right? We will take that relation between the kinetic energy and wavelength. So kinetic energy, it is to be increased 1 nanometer to wavelength should be increased from 1 nanometer means 0.1 nanometer to the 0.5 nanometers. Then kinetic energy is inversely proportional to is the square of the wavelength. Then Ke1 by Ke2. Ke1 by Ke2 is equal to lambda 2 divided by lambda 1 whole square. Therefore, Ke1 by Ke2. Ke1 divided by Ke2 is equal to lambda 2, it is given as 0.5. Lambda 1 is the 1. So lambda 1, this is lambda 2. So it's 0.5 will be equal to 1 by 2. 1 by 2 whole divided by 1 whole square. Then Ke1 divided by Ke2. 1 by 2 whole square means what? 1 by 4. Therefore, Ke2 is equal to 4 times of the Ke1. They have asked what is that additional energy. As they have asked that additional energy, we'll write that additional energy needed delta Ke is equal to Ke2 minus Ke1. So delta Ke is equal to 4 Ke1 minus Ke1. Therefore, delta Ke is equal to 3 Ke1. 3 times. These are 3 times. Next. G.P. Thomson experimentally confirmed that existence of matter waves by the phenomenon of diffraction. Okay, I'll stop this dual nature part here and I'll go for next chapter, atoms. Atoms. So in this chapter, we take that when the electron is revolving around the nucleus. So before that, we go for different theories. First to Thomson's theory, Thomson's model of the J.J. Thomson's model. According to J.J. Thomson's model, every atom, whenever consider atom, whole mass of mole mass or positive charge is uniformly distributed. Whole mass or positive charge is uniformly distributed throughout the volume of the atom. And these negative charges are embedded like seeds in the watermelon. These negative charges are embedded like seeds in the watermelon. This is J.J. Thomson's model. First model of the atom is J.J. Thomson's model. Next one is Rutherford's atomic model. Rutherford's model. According to Rutherford's model, every atom that consists of a positively charged center called the nucleus. It's called as the nucleus. Positively charged center, the nucleus. The nucleus consists of nucleons, protons, and the neutrons. The nucleus consists of called as protons and the neutrons. Around the nucleus, electrons will revolve in circular orbits. This is Rutherford's atomic model, and he has calculated size of the atom is in the order of 10 power minus 10 meters, and the size of the nucleus is 10 power minus 15 meters. That was calculated, that was given by Rutherford. So, according to Rutherford model, size of the atom is 10 power minus 10 meters, size of the nucleus is 10 power minus 15 meters. So, proton was discovered by Rutherford, as well as nucleus also discovered by Rutherford. So then to calculate this mass, size of the atom and size of the atom, they have taken one experiment called as the Rutherford's alpha scattering experiment. Alpha scattering experiment. According to Rutherford's alpha scattering experiment, they have allowed the alpha particles from the radioactive source, which are passed in the path of the light ray, means alpha particles. In the path of the alpha particles, they have placed one lead bricks. These are allowed to pass through the lead bricks. The alpha particle which are emitted from the radioactive source are allowed to pass through the lead bricks. These are allowed to pass through the lead bricks. And in the path of this alpha particles which are coming from these lead bricks, they have arranged one screen. called as right. In the path of the alpha particles which are coming, they have arranged one screen called as that gold screen. Gold foil, we used to say that. Gold foil of thickness 2.1 into 10 power minus 7 meters. So most of the alpha particles, without any deviation, they have moved in the same direction. Most of the alpha particles are without any deviation, they have passed straight lines. Very few of them, they have scattered less than 90 degrees. Few of them, they have scattered greater than 90 degrees. Out of 8,000 particles, only one particle that is that retraces its path. Out of 8,000 particles, only one particle that is able to retrace its path. So in this path, they have arranged one zinc sulfide screen, ZNS screen, and it is attached with a mobile detector. With a detector, they have arranged this. So this consists of the detector, mobile detector. This is called as the mobile detector. So then, means only one particle out of 8,000 particles that retrace its path. But most of the alpha particles, they have moved parallel, means they have moved in straight line. So then, here, if target nucleus is there, that scattering will take place. So then we calculate a scattering angle, impact parameter, the distance of the closest approach. So in this path, if I take the target nucleus is this is the target nucleus. In the path of the target nucleus, if alpha particle that comes, if the alpha particle that comes in the path of the target nucleus, then this is the alpha particle. In the path of the alpha particle, if the target nucleus is there, it will retrace its path. If the alpha particle is a little bit above to this is above this, then we'll say scattering is used to take place. Scattering, it is used to take place. Like this. Above this center line, it will be like this. Below the center line also same. Afterwards, they used to move like this. So above the center line, up to some extent, these alpha particles there is. So here the alpha particle that deviates from this actual path, it is means what? Theta is the scattering angle. So that scattered, the angle with the center line of the target nucleus is called as angle of scattering. So B is called as the impact parameter. So the perpendicular distance of initial velocity vector when the alpha particle is far from the target nucleus is called as the impact parameter. B is called as the impact parameter. It's called as the impact parameter. It is called as impact parameter. Impact parameter B is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into impact parameter B is equal to 1 by 4 pi epsilon naught into ZE square cot theta by 2 divided by half mv square. divided by half m e square. This is b is equal to 1 by 4 pi epsilon naught into z e square cot theta by 2 whole divided by half m e square. This is the impact parameter. So when the alpha particle is far from the target nucleus, it consists of only kinetic energy. When it reaches to that, it consists of the potential energy, right? From this, we can calculate that kinetic energy only converts into potential energy. Then from that, we'll calculate the radius of the, distance of the closest approach. We calculate distance of the closest approach. We will calculate from it. We'll calculate the distance of the closest approach from this. Okay. When we come to that, when the electron is revolving, next one is the Bohr's atomic model. According to Bohr's model, every electron that revolves around the nucleus in a circular orbit, like planets, how they are revolving around the sun. Then electron, even though it is revolving around the nucleus and it is accelerating, it does not radiate any energy. The next, whenever the electron is revolving around the nucleus, the whole every atom that consists of positively charged center called the nucleus, and the electrons, they revolve around the nucleus in circular orbits. Electron, even though it is revolving, it is accelerating, it does not radiate any energy. It does not radiate any energy. So when the electron that moves in an orbit in which orbital angular momentum is equal to nh divided by 2 pi. Electron, it can revolve around in an orbit in which orbital angular momentum of the electron will be equal to integral multiples of h by 2 pi. In orbit, in these orbits only, it will revolve. So when the electron is going from the lower orbit state to that higher orbit state, lower energy level to the higher energy level, it absorbs the energy. When the electron that comes from the higher energy level to the lower energy level, it emits the energy. So equal to the difference in the energies of the levels, either emission or either emission of the electron or absorption of the energy for the electron will be there. So difference in it. So when the electron is revolving around the nucleus, velocity of the electron in the nth orbit, Vn is equal to Ze square divided by 2 epsilon naught nh. 2 epsilon naught nh. This is the velocity of the electron in the nth orbit. So radius of the electron whenever taken the nth orbit, Rn is equal to epsilon naught n square h square divided by pi m Ze square. Epsilon naught n square h square divided by pi m Ze square. It will be equal to pi m Ze square. Radius of the electron in the nth orbit, epsilon naught into n square h square, epsilon naught divided by pi m into Ze square. Then Rn is proportional to n square. Then when we take that velocity of the electron Vn is equal to 2.2 into 10 power 6 meters. So 10 power 6 Z divided by n. 10 power 6 Z divided by n meters per second. Rc divided by 137 Z divided by n meters per second we will write. What is the radius of the electron in the nth orbit? Rn is equal to 0.53 angstroms into 10 power minus 10 meters. Nothing but 0.53 angstroms, which is 0.53 angstroms. Now, okay, next. radius over. From this we'll calculate kinetic energy. Kinetic energy of the electron in the nth orbit is mz square e power 4 divided by 8 epsilon naught square n square h square. This is kinetic energy. So that is 13.6 divided by n square electron volts. When we take that potential energy, PE is equal to minus m square minus m z square e power 4 divided by 4 epsilon naught n square h square. That will be minus 27.2 divided by n square electron volts. Total energy of the electron in the nth orbit, TEN is equal to minus m z square e power 4 divided by 8 epsilon naught square n square h square. TEN is equal to minus 13.6 divided by n square electron volts. Minus 13.6 divided by n square electron volts. This is the total energy of the electron in the nth orbit. This is the total energy of the electron in the nth orbit. Therefore, ratio of the kinetic energy to potential energy and the total energy is 1:2 -2:1. 1:2 like this we will take. This is that energy. So yeah, total energy of the electron in the orbits. Total energy of the electrons in the orbits, if we take that. Now, electromagnetic spectrum, whenever we take that electromagnetic spectrum, that consists of visible portion of the light is like this. This will say with GR. Visual portion of the light is with GR. The frequency of the light rays less than that of the violet are called as ultraviolet. And the frequency of the light rays greater than that of the violet are called ultraviolet. The frequency of the light rays less than that of the red are called as infrared. So whenever we take that, the frequency greater than that of the ultraviolet rays are called as the X-rays. And the frequency greater than X-rays is called as the gamma rays. So then frequency less than that of infrared rays are called as the radio waves, microwaves. And the frequency less than that of these microwaves are called as the radio waves. Like this electromagnetic spectrum is there. This is called ultraviolet region. This is visible region. This is the infrared region. This infrared region also near infrared region, far infrared region, middle infrared region, like that we'll take it. When the electron that jumps from the higher orbit to the lower orbit, it emits the energy. When it jumps from the lower orbit to the higher orbit, it absorbs the energy. Let us suppose N is taken as a 1. Then energy in it is minus 13.6 electron volts. Minus 13.6 electron volts. then n is equal to 2, that energy is minus 3.4 electron volts, minus 3.4 electron volts. So then n is equal to 3, that is minus 1.51 electron volts. Then n is equal to 4, energy minus 0.85 electron volts. So n is equal to 5, then the energy minus 0.54 electron volts. If n is equal to 6, energy is 0.37 electron volts. Like if I take for infinite orbits, whenever we take, energy will be 0. Okay, first to Lyman series. For this Lyman series, n1 is equal to 1, n2 is equal to 2, 3, so on. Then corresponding wave number or wavelength 1 by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. They will write 1 by lambda is equal to r into 1 by n1 square means 1, 1 minus 1 by n2 square. This Lyman series is in ultraviolet region. Lyman series will be in the ultraviolet region. Next, this is a transition. We say that Lyman series, when the electron that comes from any of the higher orbits to that ground state, the corresponding transitions will say that Lyman series. Lyman series is in ultraviolet region. Like this, we will take. This is that Lyman series. Lyman series. If the electron, it makes the transition from any of the higher orbit to the second orbit, maybe third to second, fourth to second, or fifth to second, like that, or sixth to second, like that, if it emits. The corresponding spectral series is called as the Bohr series. The corresponding spectral series is called as the Bohr series. Then, for the Bohr series, series, 1 by lambda is equal to r into 1 by n1 square minus 1 divided by n2 square. 1 by r is equal to 1 by n1 square minus 1 by r. So 1 by lambda is equal to r into 1 by 1. For Bohr series, n1 is equal to 2. n1 is equal to 2 and the n2 is equal to 3, 4, 5, so on. So 1 by 2 whole square minus 1 by n2 square. Yes. Next, this is the Bohr series. Next one is the Paschen series. Paschen series. This Bohr series is in visible region. Bohr series is in visible region. Next, Paschen series. For the Paschen series, n1 is taken as a 1. N1 is taken as 3. N2 will be 4, 5, 6, so on. The transitions will see that. That's transitions. If the electron comes from any of the higher orbit to that third orbit, the corresponding transitions will say past. Then 1 by lambda is equal to R into 1 divided by 3 square minus 1 by n2 square. If they say first member n of this Parsons series, let us suppose n1 is equal to 3 and n2 is equal to 4. Second member means n1 is equal to 3 and n2 is equal to 5. Like that for any series, if you take the first member, second member, like that. This is 1 by n. Next, Bohr series, Parsons series. Next one is the Fund series. This you will get in chemistry. All these will be there in chemistry, but next, bracket series. For the bracket series, the transitions are as follows. If the electron from the 5th to 4th, 6th to 4th, 7th to 4th, like that, these transitions will say that bracket series. Bracket series. For the bracket series, n1 is equal to 4, n2 is equal to 5, 6, 7, so on. Therefore, 1 by lambda is equal to R into 1 by n1 square minus 1 divided by n2 square. That 1 by lambda is equal to R into 1 by n1 square means 1 by 4 whole square minus 1 by n2 square. Like this bracket series. Next, Fund series. This bracket series is in middle infrared region. Next one is that Fund series, P silent. Fund series. This is the Fund series. In that Fund series, we'll take that n1 is equal to 5, n2 is equal to 6, 7, 8, so on. The corresponding transitions, whenever we mark them, this is 6th to 5th or 7th to 5th, like any of the higher orbit to the 5th orbit if it comes. We'll take this. This is Fund series. Fund series. For the Fund series, 1 by lambda is equal to R into 1 by n1 minus 1 divided n1 square minus 1 by n2 square. Then 1 by lambda is equal to R into 1 by 5 whole square minus 1 by n2 square. Like this will get. Okay. When the electron that jumps from any of the higher orbit to the lower orbit, it emits the energy. Then the spectral line emitted when the electron it comes from any of the higher orbit to that lower orbit, the number of spectral lines emitted is to be calculated. When the electron jumps from any of the higher orbit to that lower orbit n1, the number of spectral lines will be equal to n2 minus n1 plus 1 into n2 minus n1 n2 minus n1 whole divided by 2. If the transitions are from any of the higher orbit to that ground state, the number of spectral lines are emitted, n into n minus 1 divided by 2. See, for this Lyman series, Bohr series, this is okay. For Lyman series, Bohr series, Parsons series, if you want to calculate the maximum wavelength, maximum wavelength or minimum wavelength, then to calculate maximum wavelength or minimum wavelength, shortcut formulas are there. Here, for this shortcut formula, n represents the series number. How? For Lyman series, it is taken as 1. N is equal to 1 for Lyman series. For this shortcut formula, I am saying that n is equal to 2 for Bohr series. N is equal to 3 for Parsons series. N is equal to 4 for bracket series. N is equal to 5 for fund series. Like this. Now, whenever we take that, when the electron that comes from that maximum wavelength, lambda maximum for any spectral series, n square into n plus 1 whole square, n square into n plus 1 whole square. This shortcut formula, right? I'll dictate that. The shortcut formula to calculate wavelength of to calculate maximum and minimum wavelengths, maximum and minimum wavelengths. So that shortcut part. Lambda maximum is equal to n square into n plus 1 whole square divided by 2n plus 1 into r. N is 1 for Lyman series, n is 2 for Bohr series, n is 3 for Parsons series. Like that we will take. So minimum wavelength, if you want to calculate, lambda minimum is equal to n square divided by r. Minimum wavelength lambda is equal to n square divided by r. Like this we will take, right? So we'll come to this numericals part. If in nature there may not be an element for which the principal quantum number is greater than 4, then the total number of possible limits will be below that. As n is greater than 4, then all possible elements. So the total number of possible elements. So the total number of possible elements is equal to 2n square. This is n is taken as n is equal to 1. N we have taken it as 1, 2, 3, and 4. Up to 4 only we have taken that. Is equal to 2 into 1 whole square plus 2 into 2 whole square plus 2 into 3 whole square. That is equal to n into z square it is. n into z square it is. Two into 3 whole square plus, so n into z square, not 2 into z square. I take that 2 into n square will write. Then 2 into 3 whole square, 1, 2, 3. So 2 into 4 whole square it is. 2 into 4 whole square it is. Next. 2 plus 2 2s are 4, 4 into 2, 8. 3 3s are 9, 9 into 2, 8, 8. 4 4s are 16, 16 2s are 32. Therefore, it will be equal to 60. First one. Next. Bohr's. In the Bohr's hydrogen atom, the radius of the stationary orbit is proportional to radius of the electron in the nth orbit. Rn is equal to epsilon naught n square h square divided by pi m z e square. So radius of the electron in the nth orbit is directly proportional to square of the orbital number. It's directly proportional to square of the orbital number. Next. In that nth orbit, in the nth orbit, energy of the electron E is equal to minus 13.6 divided by n square electron volts for hydrogen atom. The energy required to take out the electron from the first orbit is the energy required to remove the electron from any orbit is En is equal to plus 13.6 divided by n square electron volts. As it is moved from the first orbit, that will take that E1 is equal to plus 13.6 divided by 1 whole square electron volts. That is equal to 13.6 electron volts. This is 13.6 electron volts. In the following atoms, molecules for the transitions n is equal to 2 to n is equal to 1, the spectral series of the minimum wavelength will be produced. So that the spectral series of minimum wavelength will be produced. Minimum wavelength means what is the formula for each? 1 by lambda is equal to r into z square into 1 by n1 square minus 1 by n2 square. Here 1 by lambda is proportional to z square. What is R? R is called as the Rydberg constant. R is 1.097 into 10 power 7 per meter. This is 1 by lambda is inversely proportional to z square. So whose atomic number is more, for that minimum energy will come. This is diionized lithium atom. Its atomic number is more. As it is atomic number is more, then minimum energy that will be emitted. Next. The Lyman series of hydrogen spectrum lies in the Lyman series that lies in the ultraviolet region. That lies in the ultraviolet region. Then the size of the atom is in the order of 10 power minus 10 meters. The size of the atom is in the order of 10 power minus 10 meters. Which one of the series of hydrogen spectrum lies in the visible region? Visible region will be Bohr series. Bohr series lies in the visible region. This visible region is not there. That is the Bohr series. Okay, visible region. Bohr series will be in the visible region. Next one. The energy required to knock out the electron in the third orbit of hydrogen atom is. So this is the third orbit means n is equal to 3. We have to take that. For third orbit, n is equal to 3. So energy En is equal to knockout means what? Remove it. Ionize like that. So 13.6 divided by n square electron volts. In this, if I write En is equal to plus 13.6 divided by 13.6 divided by 3 whole square electron volts. Then En is equal to 13.6 divided by 9 electron volts. This is positive, not negative. If the energy means what? Energy of the electron in the nth orbit means total energy, negative sign will come. But it is the ionization energy. Ionization energy is energy required to remove the electron from an orbit. Completely knock out, remove. Knockout is nothing but remove it. Next. An electron has mass 9.1 in 10 power minus 31 kc. Electron has mass 9.1 in 10 power minus 31 kc. It revolves around the nucleus in circular orbit of radius 0.529 in 10 power minus 10 meters at a speed of 2.2 in 10 power 6 meters per second. The magnitude of linear momentum in this, magnitude of the linear momentum P is equal to m into v. P is equal to m into v. Mass is 9.1 into 10 power minus 31 into velocity v is how much? 2.2 in 10 power 6. 2.2 into 10 power 6. So P is equal to this is 31 6 20. (91 into 22) to 18 to 18 and this is 1 2 110 into 10 power 31 25 minus 25 it is. So this is minus 25. Okay, we'll see this problem. It's becoming late. We'll see this problem tomorrow. For me, it's becoming late. Right, I'm going to stop the class here.